I will begin the word of prayer once I get up here. Dear Heavenly Father, we thank you for this day. I thank you for this class again, and just ask that you'd watch over us, bless our work. We pray that you'd be glorified in what we do, and that we'd all understand a little bit more about systems of differential equations today, Lord. In your name I pray, Lord Jesus. Amen. So, turning the page here, we want to talk about systems of differential equations. And to be clear, I'm talking about systems of ODEs. An ODE is a ordinary differential equation. Those are the kind we've been solving for the most part. An ordinary differential equation has one independent variable, right? And we've typically used either t for time or x, you know. And so let me just show you some examples of systems of ODEs. So example one, we might have something like x prime is equal to, x prime plus, there's no prime over here, x plus 2y, and y prime equals to 2x plus y, perhaps. Now here, it's ambiguous, but what's typically our understanding here is that, x prime is a notation for dx dt, and y prime is a notation for dy dt. Now I've been talking a little bit about a system of differential equations like this from day one in here, right? We saw these kinds of problems actually, if you can solve them. The solutions give you integral curves to the vector field, right? Like if I could solve this, it would give me integral curve to the vector field x plus 2y comma 2x plus y. So this is a system of differential equations of order 2. Another example I could give, and leave yourself some room under these because we're going to come back to these and add some things, okay guys? Another system of differential equations I could give you would be perhaps x prime is y plus z, y prime is, x plus z, and z prime is x plus y. This is a system of 3 differential equations. Your goal here would be to find x, y, and z which solve this system, right? So this is this one here is, I would say this is n equals to 2, right? This is an n equals to 3, like the number of differential equations here is 3. All right, another example might be this. We could have, y prime prime plus y equals to 0, and we could have z prime prime plus 2z prime plus z equals to 0. This would also be a system of differential equations, right? What's the difference between this and the first 2 examples? I had what? The first example I had 2 first order differential equations. The second example I had 3 first order differential equations. This one now I have 2 second order differential equations. But there's something neat that we can do with differential equations. We can always take a system of linear differential equations. These are both linear, all right? Because the dependent variables and their derivatives all appear linearly. We can rewrite this as a system of first order differential equations. Let me show you how. So if we want to rewrite this as a system of first order differential equations, we just we introduce some new variables, all right? So like the first variable is kind of boring. x1 equals to y, all right? That's not especially, I just changed the name, right? And then I'll make x2 equals to y prime. Now that's a little bit more interesting, right? So notice that we then have x1 prime equals to x2, right? And how about x2 prime? What's that equal to? Well, that's y prime prime, right? Which is, by the way, equal to, because of the top equation here, minus y. But what's minus y? It's minus x1. All right. This is the same trick we used last class to solve like y prime prime plus y prime equals e to the x or something like that. I called it reduction of order, right? If we substitute in a new variable for the velocity. Well, if we put a new variable which is the derivative of another, that's a reduction of order. So that gets the first equation, right? So I've just converted the first second order differential equation to two first order differential equations, right? And then up next here, we can let x3 equal to, you guys tell me, what should I do? How about, what do you guys think? Z, I heard a Z, I'll take it. And we're gonna let x4 equal to Z prime. So we've got x3 prime equal to, well, Z prime, which is x4, right? And we've got x4 prime, which is equal to Z prime prime, yeah? Which is what? Minus 2Z prime minus Z, right? So this last one, when I put it back in terms of the 4 and the 3 variables, I got x prime is minus x3 minus 2x4. So let me summarize what just happened. I took two second order differential equations and I recast them as four first order differential equations. Now, this is not a proof space class, but I'm going to tell you, you should believe me when I tell you, if I took a list of linear differential equations, each of particular orders, right? Then if I take those, I can do this reduction of order thing, and I can convert them all into first order differential equations, right? Where the net number of differential equations is the sum of the orders. I had two 2's, 2 plus 2 is 4, I got 4 first orders, right? Okay, so we can do this trick. So what does this all mean? This means that if we can solve an arbitrary first order differential equation, we have solved any linear system of differential equations. And that's what we're about to do. We're about to learn how to solve any system of differential equations. At the moment, these are homogeneous. We'll eventually circle back and solve non-homogeneous problems, all right? But let's first focus on the homogeneous case, all right? Now, do you guys have any ideas about how we could do this? Like if you knew nothing about linear algebra, if you knew nothing about matrices and all that, which is some of you guys, right? Not really, everybody should know something about matrices from high school, right? Anybody not have some matrix exposure at high school? You didn't? Ah. How about you seen that? Okay, good. But since high school, things have got, okay, good. I was worried for a second there. So we're going to use matrices shortly, but suppose for a second you never knew about matrices. Well, the way you'd solve these would be to play games to like eliminate variables, right? You try to make it just about one variable and not several, but that would actually be a complicated business, really, yeah? So it's good that we actually have a matrix technique and we'll let the linear algebra do the separation of variables for us, basically, all right? So the first order of business is to understand how to write the matrix of a system. So what we do is I'm going to introduce like a variable of variables. Let's call it R for the sake of discussion here. R will be, in this case, xy, all right? And I want to rewrite this, and so what would dr dt mean? Well, you guys have had Calc 3, so you know it's x prime, y prime, right? The derivative of a vector is the vector of the derivatives. Okay, so look, I can take this system here and I can repackage it as dr dt. I'll write it in this notation to start with. You got x prime, you got y prime, right? And you can write it, I'll get right to the point. You can write it as the following matrix. 1, 2, 2, 1. And then my vector of variables over here, x, y. Do we see the where those numbers are coming from? I'm coming from here and just reading off, there's a 1, there's a 2, there's a 2, there's a 1. So this is the matrix of coefficients for this differential equation, right? And if I just summarize what's going on here, we've got dr dt is equal to a matrix A times R. All right, that's the system in so-called normal form. Maybe it's standard form, I don't remember. It's a form anyway. That much we can all agree, I hope. Oh, hey. Let us all count ourselves as attending. What's today's date? All right, good. Here, I'll start this somewhere. How about over here? So you guys tell me, what's the matrix of the second problem here? What would that be? So we'd have what? We'd have x prime, y prime, z prime equals to what? We could... So you got to choose an order of the variables. So I'm just going to do x, y, z because, you know, what else would you do? I've got to vote for 0, 1, 1, I think. Cool. How about the second row? 1, 0, 1. All right, great. Next up. 1, 1, 0. Hooray. Yeah. And so I would call, this is what I usually call A, the matrix of coefficients, right? And here, in this context, my vector of variables would be x, y, z, right? So again, what is this problem? It's dr dt equals to what? AR, right? Where I'm using a so-called matrix column vector multiplication. Do you guys see how to form the matrix column vector multiplication? Should I do some examples of that? I mean, I can do some examples. I think these are kind of examples. I decided to make the examples based on differential equations as opposed to just linear algebra because that's kind of our application here, so yeah. How about this next one? x1, x2, x3, x4. I'll put them in order, yeah? Prime, prime, prime. Equal to what? And I like to put kind of like dividers in when they're big, just to keep myself kind of straight. So let's look at the first one. X prime is equal to x2. What's that do for me? What? Oh no. Yeah, I did do that. Thank you. Hey, let's mix it up. Newton's notation. Dot for derivative. Yeah? Okay. I've now angered the math majors. It's okay. Okay, so then what? What's the first column? I mean, column, let's see. What's the first row? 0, 1, 0. So there's no x3 or x4, which puts this here. Now, let me just kind of, let's finish this example, then I'll do another one. How about the second row? We get what? We have -1, 0, 0, 0. All right. Then what? For the purple equations, we got ourselves x3 prime is x4, right? That puts a 1 here, and everything else is 0. All right. x4 prime, what do we got? Well, 0, 0, -1, -2. All right. And there you go. That's the matrix. Again, this has the form dr dt equals to a times r, right? But here our vector is x1, x2, x3, x4. Are we good so far? Let me work an example the other way around. Example 4. Suppose you've got r equal to, I don't know, x, y, z, and you've got a is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. All right? What does it mean to write dr dt equals to AR? What does that entail? So this is the matrix form of the differential equation. So what I want to talk about now is let's find the scalar form of the system. So my first three examples, guys, they were all beginning in scalar form, right? And then I converted them to matrix form. Now I'm going the other way around. Start with the matrix form, convert to scalar form. So what do we got here? We've got, x prime, y prime, z prime is equal to, apparently, 1, 2, 3, 4, 5, 6, 7, 8, 9 times the column vector x, y, z. How do we multiply a matrix times a column? Let's talk about it. So what it is a dot product, right? So what we got is actually the dot product of the 1, 2, 3 vector with the x, y, z vector, right? And then the dot product of the 4, 5, 6 vector with the x, y, z vector. Then the dot product of the 7, 8, 9 vector, I will get out of the way in a second here, x, y, z vector. Right? That's how we calculate a matrix times a column. It's the dot product of the column with the first row for the top spot, the dot product of the second row of the matrix for the middle spot, the dot product of the column it's multiplying by the third row for the third spot. This is how we multiply a matrix times a column. It's dot products. And of course, you can calculate those dot products and you got yourself x plus 2y plus 3z, 4x plus 5y plus 6z, 7x plus 8y plus 9z, right? This is still a differential equation, I would argue, in matrix form, right? It's just a kind of, but you can easily see how to write the system in scalar form, right? How do you do it? It's kind of silly, but here it is. X prime equals to x plus 2y plus 3z. Y prime equals to 4x plus 5y plus 6z. And z prime equals to 7x plus 8y plus 9z. There you go. This is the system of differential equations, bless you, in scalar form, right? So if I ask you to write the answer in scalar form, what do I mean? I mean write x equals to blah and y equals to blah, right? If I say write the solution in vector form, I mean you should write it as a vector, right? But here we're just talking about the form of the differential equation, like a scalar form versus a vector form. I suppose this, you could argue, is the vector form of the differential equation, right? So here we have vector form, scalar form, matrix normal form, all right? If you have the feeling these are all the same thing, great. That's what I'd like you to think. But I'd also like you to be able to answer, if I ask a question specifically, please give the answer in such and such a form, then do try to do that. Otherwise, you're just free to give the answer in the way which is most convenient and illustrative of the fact that you understand what you're doing, So the biggest issue with that is like sometimes we're going to use a complex technique, and it's almost never the case that I want the answer as a complex answer. I almost always want, we keep it real in here. So we're looking for real answers. And so like that's going to be an issue sometimes because you guys just give me complex answers, which is like, that's nice, but you need to finish the job, right? That's not the full answer. So how do we solve these? Any ideas? So let me explain what I'm doing here. In past years, I've taught differential equations. Sometimes I take a half hour just to teach matrices and linear algebra. And we could do that, but I think it might be more useful for me to just teach the linear algebra and matrices as it comes to us in the differential equations problems. So that's the format I'm adopting this year, all right? If you want to see a standalone hour about just how matrices and how do you solve them and stuff like that in the context of this course, any number of past years will have that lecture, okay? So, of course you could also come to office hours. And I'm just talking, how many, show of hands, who said 221? So you guys are bored out of your mind a little bit. Or you're in 221. Okay, well, yeah, you're not bored yet. Okay, so here's some systems. Let me just share some theory with you, okay? So here's the theory, theorem. If, let's say dr dt is equal to, a vector of r and t. So what I'm saying is this is a linear, and I really should even, well, we'll keep it homogeneous for a second here. Linear system of n homogeneous ODEs, all right? Then there exist n linearly independent solutions, and by that I mean like dri dt equals to f of like ri comma t, I equals to 1, 2, da 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 n. And we don't have to, well, I mean, I can tell you how to judge linear independence of solutions, but let's not get into the weeds right now. We'll come back to that later. It's just saying that, for instance, like the most basic example of this is like, we would not like to say a given solution and twice the solution is the same solution, right? That wouldn't be productive. We need a way to categorize solutions being independent, right? And so the technical criteria for that is linear independence, all right? So if we have these n linearly independent solutions, and what that means is that when you plug them in, they solve the differential equation, all right? So like, for the examples we've looked at, every one of these has just been a constant matrix times a vector, right? Like my formula for f of RT has been what? It's just been a constant matrix times R, right? For all of the examples we've done, A has been a constant matrix times R vector, right? But this theorem I'm writing, it also holds when the matrix has like functions in it. So the system could be more interesting. It could have like a function, like a time dependence in the coefficients of the differential equations. Anyway, so if you have this, so the theorem is there exist n linearly independent solutions, and the general solution has form R equals to C1 R1 plus C2 R2 plus dot 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 plus Cn Rn, right? All right. The general solution is what we're after, all right? we'd like to find the general solution to these problems. Now, if you want to find, if we were given initial conditions, right? Then instead of finding the general solution, we could try to find a specific solution that's tailor-made to fit those initial conditions. And there's also a theorem that says that's always possible in this context, because we're assuming we do assume this is like continuous, all right, even smooth, let's say. Okay. So given given a decent condition on the differential equations themselves, basically that the coefficient functions which appear are nothing too nasty, it turns out that, yeah, there's a unique solution to every initial value problem, right? And, but for the time being, let's look for general solutions, all right? So what does this mean? What are we looking for? We're looking for every one of our differential equations. Our goal, our mission, is to find what? So for like a problem with 2 differential equations, we're looking for 2 linearly independent solutions, right? For a problem with 3 differential equations, we're looking for 3 linearly independent solutions. For my 4x4 example, we're looking for 4 linearly independent solutions. You get it? So I guess I do feel bad to not tell you what linear independence means. So let me just, I will not resist that forbidden fruit at the moment. So actually, remark, to test linear independence of solutions, we can check the Wronskian. What on earth is the Wronskian? So I should derive this another day, but I'm just dropping some knowledge on you here at the moment. And so like W of R1, R2, Rn at time t is equal to the determinant of R1, R2, Rn. So to check the linear independence of n solutions, what you do is you just take the solutions, you glue them into an n by n matrix, and you calculate the determinant, right? So now we've reached a slightly more technical point. Who here knows what a determinant is? Who here is not sure what a determinant is? All right, so we got to define these, right? So let me show you some examples then, yeah? What is a determinant? So let's see here, example 5. Let's suppose we have R1 equals to e to the t times 1, 2, and R2 equals to e to the t times, let's say 3, 4, okay? So we can check, are these 2 functions linearly independent? Let's work it out, okay? So the Wronskian of R1 and R2 would be the determinant. All right, now I need to do a little bit of matrix math here. How do you multiply a vector times a scalar? What do? You just multiply it into both spots, right? So like R1 is e to the t, and then 2e to the t, right? And this guy over here was 3e to the t and 4e to the t. I owe you a definition of the determinant because not everybody in here knows. Well, that's not entirely true. You've all had calculus 3, so you actually do know the determinant for at least a 3 by 3 because you've calculated the cross product. And the cross product formula is the determinant. So, it's one of the hidden taxes of being short. Oh, man. Not good for the eyes, this stuff. It's not good. It also tastes bad, for the record, but not today. I didn't taste it. So just as a general point of order, here's the determinant of a 2 by 2 matrix, A, B, C, D. The determinant is simply A times D minus B times C. So you need to know this, all right? So when I put that into practice here, I get what? I get e to the t times 4e to the t minus, 3e to the t times what? Times 2e to the t. Okay? Which is what? 4 minus 6 is, minus 2. So I got minus 2 e to the 2t. That's the Wronskian here. Is this non-zero? Can this be 0? No. Although that's kind of a misleading question. The Wronskian being 0 at one point. Well, anyway, let me not get into that right now. So this this is not equal to 0. So thus, therefore, R1, R2 are linearly independent. Now, notice that if we were just in a one-dimensional problem, if both of the solutions were just based on e to the t, they would necessarily be linearly dependent, right? If I had like y1 is equal to 2e to the t, and I had y2 is 10e to the t, well then y2 is just what? It's 5y1, right? This would be a linear dependence. In other words, the solution y1 and y2, they're not independent, right? But when we're dealing with a two-dimensional problem, you see we can have an independence between two solutions which are just based on an exponential of t. That was something that couldn't happen in one dimension, but it can happen now. All right, so next up, example 6. Let's look at R1. So I'm just going to do numbers for a change, if you guys don't mind. So suppose I've got 1, 2, 3 for my first vector, and then, I don't know, 4, 5, 6, and then I'll make it a little bit easier on us, 0, 1, 1. And I want to check if these three vectors are actually linearly independent. Okay? So I could do that. Let me put a t on this one and a t squared to make it more relevant. Let's see here. What's that? All right, so I'm going to check linear independence of these three functions. All right, so I wanted to illustrate the 3 by 3 determinant here. So I'm going to call this one R1, R2, R3. All right, great. So the determinant of R1, R2, R3 would be the Wronskian of these three. So we're looking at the determinant of apparently 1, 2, 3 for my first column, 4t, 5t, 6t for my second column, and 0, t squared for my third column. I guess I owe you guys a formula for the 3 by 3 determinant, right? So I'll put it over here. If we have the determinant of A, B, C, D, E, F, G, H, I. All right, here we go. It is A times the determinant of E, F, H, I minus B times the determinant of D, F, G, I plus C times the determinant of DE, GH. This is so-called Laplace's expansion by minors. And but you already know what these mean, right? Because we already defined the 2 by 2 over here. So that's how it goes. Do you guys know how to calculate the determinant of a 4 by 4? Let's look at it. What if I had determinant of, I'll use numbers this time, A11, A12, A13, A14, A21, A22, A23, A24, A31, A32, A33, A34, A41, A42, A43, A44. I'm starting to regret this. All right. So this is a 4 by 4 matrix. All right. The determinant is, well, A11 times the determinant of A22. I don't want to write this all out. Oh, man. I'm going to start it. All right. You're bad people. Let's see here. All right. So anyway, I'm gonna use my words next time. A12, determinant of, A without row 1 and column 2. 3 by 3. Plus A13 times the determinant of A without row 1 and column 3. Minus A14 times the determinant of A without row 1 and column 4. So you always cross out one row and one column, and it leaves you a submatrix which has one size less. Yep.
Do you need to go to that? Can you just go like straight from the third level? Can you just multiply the AEI minus?
So you're thinking of the trick that's known for the 3 by 3 matrix, which goes like this. If you lay out the matrix twice in a row, I don't believe such a trick is known for the 4 by 4. That's special to the 3 by 3, which is great if you know it. But yeah, there are many other tricks, right? Like you can expand about any row or any column. Like the same, I could just as well have done like, A13, determinant of row of A without row 1 and column 3, minus A23. Actually, I got to check here. Plus, minus, plus. Okay, yeah. You have to think about the way the expansion goes is based on this sign pattern. So like whenever you do an expansion by cofactors, either across a column or a row, you have to take into account these signs in the expansion. It's where that annoying minus comes from on the J hat thing in the vector in the cross product. That always gets you guys in that other course. Okay, so determinant. So this is A without what? Row 2. Rather row. My bad. Row 2 or column 3, and then plus A33, and then determinant of A without row 3 or column 3, minus A34, determinant of A without row 4 or column 3. You notice the difference in the pattern here. This is the column expansion. I'm expanding the determinant down this column against determinants of the submatrix formed by deleting always the third column in either the first, second, third, or fourth rows. Anyway, I mean, we could talk for 3 weeks about properties of the determinant. They're endless, all right? But if we just know the expansion by minors, that should suffice for us in here. Yep.
So all these where you write a solve and then you have the smaller matrix, and that's like just a placeholder, right? Because then you still need the cross product between those smaller ones.
Well, yeah, I mean, of course, in doodly doodly. This, we still have to expand this, this, and this. This, every one of these 3x3s, you're right, you had to go back up to here and do this. Yeah, yeah. Yeah, woo, indeed. And so, it's bad. It's very bad. That's right, yeah. But the good news is we're just going to put a variable here and solve a polynomial equation that results from it. So, you know, it's not too bad. Fortunately, there is technology. I typically only test you guys on like the 2x2 case. So in terms of testing, pretty much on the test it's going to be this. In your homework it's going to get worse, right? But if I do ask you a bigger determinant formula question on a test, it's got to be like a nice special pattern. So one of the super nice special patterns, and I'll tell you this, is if you have the determinant of like a matrix that looks like this. So this is a so-called block diagonal matrix. Right? Something beautiful happens. It's the determinant of the product of the blocks. So that's pretty awesome. That's one thing that's vastly simplifying. The other thing that's vastly simplifying is if you've got a triangular matrix. So like you've got C1, C2, let's say D1, D2, da da da, Dn down the diagonal, right? And then stuff up here, whatever. This determinant, straight up, the product of the diagonals. So here's 2 ways I can make determinants like way easier on a test. I can make the matrix block diagonal, so you just multiply the determinants. I can make the matrix diagonal, either upper triangular or lower triangular. This is an upper triangular, right? So I'm saying it's 0 down here. But if it's either if it's either upper triangular or if it's lower triangular, you can just multiply the diagonals, and that's the determinant. So these are some shortcuts. But it is true, in general, you definitely want to use technology to calculate a determinant, like no doubt. Because in general, an n by n matrix, the computation of the determinant goes like n factorial. I'm sorry, n factorial. There, it's better. It's an exclamation point. You should say it out loud. You know? But, so you guys know from your circuits course that you can solve Kirchhoff's laws with Kramer's rule, right? No? You guys been taught Kramer's rule?
From Seinfeld?
This is, I used to think that, but it's not about putting in levels. It's about Kramer with a C, not with a K. It's, I know. I don't know if his first name was also Cosmo. That would be fascinating. I really don't know, but some British student named Kramer. He's got a method for solving a system of equations called Kramer's rule, and it involves taking the ratio of the determinant of the coefficient matrix with the coefficient matrix with the inhomogeneous term swapped out. That's a really bad method because determinants, computationally, cost n factorial steps to solve, right? The other method for solving systems of equations, which we're going to get into here, is row reduction, right? And that costs more like n squared steps. So row reduction is a far superior method for solving systems. We need both in here, though. We do need determinants because we have to understand something called the characteristic equation. All right. So let me show you where that comes from. So oh man, I don't want to erase those. I gotta erase this. Oh. Yeah, I should probably finish. How do I get distracted? Oh, that's that. It's all you guys' fault. So that's 1 times 5t cubed minus 6t cubed minus 4t times 2t squared minus 3t squared and 0. So lo and behold, we got ourselves a minus t cubed plus 8t cubed, I think. And so I think that's a 7t cubed, right?
No.
Because you have a minus
Yeah.
4t times a minus t.
Yeah.
The term on the right should be 4t cubed instead of 8t cubed.
Oh, thank you. That's 3.
Yeah.
Okay, so long story short, these are linearly independent.
When t is not 0, right?
T equals 0 is actually not a problem.
I guess it's
The funny thing here is we're judging linear independence of functions. So if there exists a time where it's non-zero, it suffices for it to be linearly independent. This is a fussy point that's really more for linear algebra students than... We'll get back into that. There's something called Abel's formula, which answers the thing you're raising. But we should focus... I'm going to focus on the deeper question here at the moment. Not deeper, the more surface level question, which is how do we solve these things? Right? So let me just show you how we solve these things. I mean, I'm not going to answer it entirely today, but I'm going to get us started. So we're trying to solve, let's just look at it from, excuse me, goodness gracious, 3 minutes. Wow, this is tough. All right, watch this, guys. We're trying to solve dr dt equals to AR. We'd like to solve this, right? So here's what we do. We guess solution has form R is equal to e to the lambda t times a constant vector u. All right. If you've had this class before, you might have used e to the rt, you know, sometimes used instead of e to the lambda, but I like lambda. All right. If that's the solution, how do you judge if it's a solution or not? Plug it in, see if it works, right? So if we calculate dr dt, what do we got? What's the derivative of e to the lambda t? It is lambda, e to the lambda t. And if this vector u is constant, it just rides along for the derivative, right? So that's straight up the derivative of my proposed solution. On the other hand, it's going to be equal a times r, which is what? A e to lambda t u. So what does this mean? Well, e to the lambda t, is it ever 0? Search your heart. The answer is no. So we can divide by e to the lambda t without loss of generality. And this gives us the lovely equation lambda times u vector is equal to au vector. I don't know if you know this or not, but this means that u is an eigenvector of A with eigenvalue. Lambda. Let me tell you a little bit more. We can rewrite this as A minus lambda times the identity matrix, U equals to 0. So this identity matrix I'm talking about, in the 2 by 2 case, it's like this. For example, the 2 by 2 case, that's the identity matrix. So I can rewrite it like that, all right? And in short, we have this matrix, A minus lambda I, times a vector. Now, to make this interesting, do we want u to be 0? If u is 0, that's not interesting. 0 is a solution. We're not after that, though. We'd like a non-zero solution, right? So to have a non-zero solution, we must have u not equal to 0. Okay? we're going to assume u is not equal to 0. If that's the case, what that means from the theory of linear algebra, that implies that the determinant of a minus lambda I has to be equal to 0. This, my friends, is the so-called characteristic equation. And so the way this works is the following. You write down the system, you find the matrix of the system, you write down the characteristic equation, you solve it, you find the eigenvalues. From those, you find the eigenvectors, and that gives you solutions, so-called eigensolutions. You take a linear combination of those, like I told you in the theorem over here, that's a solution, when it works. So we'll look at when it works next time, and then we'll see when it doesn't work. Yep.
Who's eigen?
Who's eigen? Eigen is just eigen is like a self value. It's like a proper value or something like that. So in German, eins is like 1. So like eins element. So this is it's like a 1. I don't know. It is a German word. You know, they used to kind of rule the world and stuff. So mathematically speaking, back before World War II, Göttingen was like Princeton.